Hello, I'm Clint Panion. I'm in Mr. Wood's ME350 Thermodynamics course. This is the third warning assessment. I'll be presenting how to do number one. Let's read the problem. Derive Bernoulli's equation starting from the rate energy balance equation. Assume the system is a controlled volume system and has negligible heat loss. So the equation we're starting at is Bernoulli's equation. If you've ever done any engineering involving fluids, you probably run into this equation at one point or the other. So what it is pressure at state one plus rho V1 squared over 2 plus rho G Z1 is equal to pressure at state 2 plus rho V2 squared over 2 plus rho G Z2. So you're basically looking at the pressures, kinetic energies, and potential energies at state 1 and comparing them to state 2. And the equation we're trying to turn this into is the rate energy balance equation. It is dE control volume over dt is equal to Q dot CV minus work dot control volume. This is like heat transfer, this is work, plus the summation of mass flow rates into it times internal energy, kinetic energy, potential energy, and then the exit. So you can kind of see the skeleton of Bernoulli's equation already in the rate energy balance equation. The stuff that sticks out is this internal energy and this Q dot, but it's not an issue because we are told that it has negligible heat loss, so that just means heat transfer is going to cancel out. And if we're doing this, we're going to assume that energy in is going to be equal to energy out, which cancels this. And one of the rules, we're going to use a couple of rules that are specific to Bernoulli's equation to help cancel things out. And one of those starting off is going to be no change occurs in internal energy. Let's start that. And so that's going to justify why the specific enthalpies get canceled, because those are supposed to represent internal energy U in the rate energy balance equation. All right, so let's just write everything out again with our canceled stuff gone. Minus work dot control volume plus. This summation really doesn't add anything in this scenario. We're just going to assume there's only one initial mass flow rate and one exiting mass flow rate. So this is kinetic energy plus potential energy initial plus kinetic energy exit plus potential energy exit. All right, so we can see that we have kinetic, we have potential. Those are here. So where's the pressure come from? Well, this is the part where we start messing with this work control volume. So work can either be measured in, it's PdV or VdP. So since Bernoulli's equation has this changing pressure at state 1, state 2, we're going to use the VdP version. So yeah, work is equal to this. So this is going to become work is equal to V times P exit minus P inlet. Now, we are told that density is, in Bernoulli's, another standard for Bernoulli's is that density is constant. And we're going to bring density into the formula by messing with the volume. So we're just going to turn volume and make it in terms of mass over density. So now when we redistribute everything, work dot CV is now going to become mass over density P exit minus P inlet. All right, so now we're gonna rewrite everything again. We're gonna have mass over rho P exits minus P inputs plus mass flow rate I BI square over 2 plus GZI. All right, so we have pressure here. So the only thing that's really sticking out now is mass flow rate and all the masses and everything. So again, we're told that this is a control volume and that it's in a steady flow system. So the way I interpret this is that mass flow rate initial or into is going to be equal to mass flow rate exit. And it's just going to be equal to the just one mass flow rate. And if density is constant, that must mean that the mass is constant. And this is just a way of justifying why all these masses are just going to cancel out. So now we're going to rewrite everything again, but now we're going to move everything that's into E and I to opposing sides. So, oh, this was supposed to be negative. Yeah, in the workup here, that was negative. So I'm just going to distribute the negative now. Negative PE plus PI. So I'm just going to move everything to the same side. So that leaves us with PI over rho plus VI squared over 2 plus GZI is equal to P exit over rho plus VE squared over 2 plus GZE. Okay, now before I redistribute the density, I'm going to say that I is going to be equal to state 1, and E is going to be equal to state 2, like 0.1, 0.2. All right, so now I'm going to multiply everything by rho. So now we're going to have P1 plus V1 squared over 2 times rho plus rho G Z1 is equal to P2 plus rho V2 squared over 2 plus rho G Z2. And that's how we transform the rate energy balance equation into Bernoulli's. Just a reminder, the key rules that we use to create this transformation were a steady flow system, density is constant, and no change occurs in internal energy. And that's the gist of it. I hope you enjoyed.